But who is my neighbor? So we're going to look at nearest neighbor methods and what it means to actually define neighbor. Big data is often complex, high volume, high variety, high velocity, and the complexity tends to imply an underlying topology. High variety topologies, on the other hand, are often modeled by networks. Nearest neighbor methods construct a network model from a set of data that hopefully is a good representation of the underlying topology. Emphasis on hopefully. Let's take a look. Suppose you have structured data and a new observation. You want to choose a method for determining how similar two observations are, find similar observations in the original data, predict information about the new observation, the unknown, using these similar observations. So you find, using some criteria for similar, something in the original data that's similar to the new, and you use what you know to make a prediction. For example, suppose a data set is structured in numeric. A similarity kernel is a function that returns a similarity score given two observations. Before we get into that, let's relabel the observations and the features. And then let's look at vector notation for the observations. So we use a bold lowercase letter to denote a vector. It's a list of coefficients or numbers. The coefficients are denoted as ordinary instances of variables. In vector notation, we have our vector bold X is either a list, or sometimes we use the angle brackets for vector notation. Observations, therefore, are vectors of instances of features. And the set of all vectors within coefficients is denoted Rn. And vectors of feature coefficients are called feature vectors. And the Rn, when it's used as a model for feature vectors, is sometimes called feature space. Similarity kernels are functions of two variables, x and y, two observations, that return a score of how similar two observations x and y are. Sometimes we call it the affinity between x and y. It includes correlation as a special case, and sometimes we say similarity is generalized correlation. Later in the course, we'll also require that our kernel functions be positive definite, which is closely related to positive definite matrix from a field known as linear algebra. But in many applications, similarity is just a conditional statement, a statement that's either true or false. And then very often we'll use numerical values. So k of xy is 1 if the condition is true, and 0 if the condition is false. For example, let's look at a problem known as the subeconomy problem. A subeconomy of a microeconomy is a subset of households that rely only on a common set of businesses. They don't have any activity at other businesses. Each household's monthly transactions is represented here with this set of data. Notice we're not doing any e-commerce. Nobody's buying anything online in this example. So notice household 1 works at business 4. They earn their money at business 4 and they spend it at businesses 1 and 3. And so we see an example of a subeconomy with households 1, 4, and 5. So these are households that frequent a common set of businesses. Now, how would we find the largest subeconomy? Well, there's a direct approach. Just take a subset of households and see if they form a subeconomy. So you got some subset, but notice household 2 does not interact with business 3, but household 5 does. So therefore, household 2 and 5 do not form a subeconomy. but households 1, 4, and 5 do form a subeconomy. So just generate all the subsets of the households and check to see if each subset is a subeconomy. And of all those that are subeconomies, the largest is our largest subeconomy. For example, suppose we had a small town with 250 households, that'd be about 700 people, and about 20 businesses. To find the largest subeconomy, you just simply check each subset using the direct approach. However, even on the Titan supercomputer, which could process this many subsets per second, you're still looking at 1.8 times 10 to the 75th subsets with only 250 households. That's 5.73 times 10 to the 52nd years on the Titan supercomputer. But if you were in a town of 700, you probably could just say what the subeconomy was on your own. There's only 20 businesses. They pretty quickly could figure out that there's some people that only frequent this set of businesses. So the direct approach is too slow. Same approach as the subset sum problem. It ignores the structure of the data. So let's use graph theory. Each household will be a node or vertex. So what do I mean? Well, a graph, a simple graph, is a set V of vertices or nodes along with a collection E of edges of two-element subsets of V modeled by line segments. No vertex is paired with itself, can't have self-connections. No edge occurs more than once, no multiple connections. So, for example, these would be edges, and this would be a graph with these vertices and the edges so drawn. Now, a kernel should model the subeconomy relationship between two households. So if households X and Y form a subeconomy, then KXY is true, otherwise KXY is false. It's very easy and quick to calculate KXY. Take Johnson and Brown. Easy to see that their zeros are in common, and easy to see that Smith and Johnson, for instance, just look at Rivers Auto, easy to see that they do not form a subeconomy, this pair. Williams and Miller, on the other hand, do form a subeconomy. Brown and Davis form a subeconomy. So now we have the ability to find pairs that form subeconomies. If KXY is true, then there's an edge between X and Y. So Johnson and Brown, true, so there's an edge between Johnson and Brown. Smith and Johnson, false, no edge between Smith and Johnson. Williams and Miller, true, therefore, an edge between Williams and Miller. Brown and Davis, true, you have an edge. Johnson and Davis, true, you have an edge. Now let's do a few more definitions. Suppose we have a simple undirected graph. If you have an edge in E, the set of edges, then X and Y are said to be adjacent, written with X and then the sim sign Y. The neighborhood of a vertex is the set of all other vertices in V that are adjacent to X. The degree is the number of neighbors in the neighborhood. A path of length n is a subset of vertices in V such that each next vertex is adjacent to the previous. Subgraph is a subset U of V along with two element subsets of U that are also in E. Now suppose in our simple illustration we remove this edge from X3 to X4. The result is two subgraphs. They're both subgraphs, but they're not connected. So we say that they're each a component of G prime. The largest connected component has 5 vertices, And so that leads to our definition of connected component. Any two vertices in C are in a path in C. The neighborhood of any vertex in C is completely contained in C. So the largest subeconomy is the largest connected component of the resulting subeconomy graph. In this case, Johnson, Brown, and Davis. Now that still leaves 31,250 vertex pairs to test, but you can do this pretty easily on a laptop or even a cell phone. And the linear component can be found in linear time. So now we have a very quick way of identifying subeconomies. So let's look at the small town data and see how it actually works. So here's household Smith and Johnson and Matthews. We create a Python function called isSubeconomy to implement our kernel function. There you see it. It's true if they form a subeconomy, returns a 1 and false otherwise. So is Smith and Johnson a subeconomy? Well, no. You can just look at town foods. Is Johnson and Matthews a subeconomy? Well, it turns out that it is. So now we can create the subeconomy graph. We take the households, create a graph using the households as vertices, and then we look at the subeconomy graph, and that's not very satisfying. The problem is that we have a whole lot of small subeconomies, but no one big subeconomy. So no subeconomy here has more than 5 households. The problem is that the data is messy. So let's look at the messiness in the data. There are a lot of monthly transactions that are small, less than $100 a month. And those small monthly transactions are what are keeping us from finding a large subeconomy, a single large subeconomy. So you can see those small transactions. There's lots of less than $100 a month expenditures. For instance, Johnson buys 1 item a month from Acme. Brown stops at the Smart Mart maybe a couple of times a month at most. So we can threshold the data that maps values that are less than 100 to 0. So we apply that, and now we have a modified set of data. In other words, this is pre-processing. How did we know 100? This was all exploration. But we do end up with one large component. In fact, the largest subeconomy is a set of households with these names. So nearest neighbors compare observations via a kernel function known as similarity or affinity. Nearest neighbor similarity defines a graph. Graph's another word for network. Similarity is another word for affinity. Now, only rarely does a network representation capture all there is to know about a data set. So remember, the word was hopefully. Pre-processing is almost always required.